All right, good morning, everyone. Today, we're going to hit our last chapter for the term. This is chapter 19. It's going to be regarding the nervous system. Now, the nervous system is a fantastically complicated system. It's probably the most complicated system in the human body, mainly because I think it's kind of abstract. It's hard to really conceptualize what it looks like. But what we're going to do is really, obviously, as we have done, stick with how it interacts with and influences exercise. So there's really three major topics that I'm going to highlight in this PowerPoint. This PowerPoint's only 35 slides, so again, I trimmed it down pretty well to really just focus it in on what we need to learn in this class with regards to how exercise is influenced by the nervous system. Okay. So before we get to the first of those three topics, there is a little bit of introduction I want to do. So there's a lot of subdivisions of the nervous system. So the first subdivision that we will make is to divide the nervous system into its first two divisions, and those are the central nervous system, which we abbreviate as the CNS, and the peripheral nervous system, which we abbreviate as the PNS, okay? So the CNS is your brain and your spinal cord. I like to look at it as this is the central part of your body, so the central nervous system is located in the central part, brain, spinal cord, okay? Then the peripheral nervous system is everything outside of that. So out in the periphery, which is like away from the middle, are located all of the other nerves, right? So every nerve, once something leaves the spinal cord, like a major nerve leaves the spinal cord, then we get into the peripheral nervous system, okay? So those are the two main subdivisions of the nervous system as a whole. Here we can see, again, in a picture, we have the CNS here. And then once these nerves start to come through the spinal column, then we get into the peripheral nervous system, right? So all of our organs, our skin, our heart, muscles, they are innervated by the peripheral nervous system. And within the peripheral nervous system, there are some other subdivisions as well. And those are initially shown here, but that's our first of our three topics that we're gonna get into, is this initial division within the peripheral nervous system. Okay, so that's going to take us to here. So within the peripheral nervous system, we have what is known as the efferent division, okay? And then we have the afferent division. Now, I'm not going to worry too much about you all remembering the difference. However, it is worth noting, afferent is ingoing to the central nervous system. So all of your sensory information travels back towards the brain and spinal cord via the afferent, with an A, division, okay? And then over here, the efferent division is outgoing information from the central nervous system to the rest of the body. So why they chose two words that are so similar, I don't know. It's kind of frustrating. Afferent is incoming, efferent is outgoing, okay? So within the efferent division, we have some things that are very important for exercise. That's going to then take us to our next division. We have our autonomic, somatic, okay? Now the key difference with these two, autonomic, think of that as autonomic, automatic. When something's automatic, we don't have to think about it, right? So the autonomic nervous system is a part of our nervous system that functions outside of our conscious thought, okay? Because it controls things like the speed of your heartbeat, the speed of your breathing, etc. We don't think about those things. They just happen. Adjustments are made automatically by the autonomic nervous system. Then on the other side of that, we have the somatic nervous system. So this is voluntary control, okay? So the main thing that our somatic nervous system controls is the contraction of our muscles. So we do have to think about that and make it happen, right? So again, both of these are going to be outgoing information. One is not conscious, the autonomic nervous system. The other is conscious, somatic nervous system. Now, our first major topic is the autonomic nervous system, okay, which again can be divided into two subcategories. We have the sympathetic and the parasympathetic, okay? So the sympathetic nervous system is abbreviated as the SNS, parasympathetic as the PSNS. Now, these colors, I think, were probably done intentionally. Green means go, red means stop. The sympathetic nervous system prepares your body to go, okay? A lot of people refer to the sympathetic nervous system as the fight or flight system because it gets your body ready to either fight for your life or to run for your life. Either way, it's preparing you to go, right? The parasympathetic, red means stop. The parasympathetic nervous system prepares your body to relax and rebuild. Some people refer to the PSNS as the rest and digest system. As we'll see, digestion is not a priority when you're fighting for your life. Digestion occurs when you're resting, right? Your body only has so much blood to send to different tissues, as we saw last chapter, right? When we're exercising, blood is diverted towards your muscles and skin and away from your digestive system. While when we're resting, blood is diverted away from muscles and towards the digestive system because your body has to kind of make a decision. What is the priority right now? Wherever the priority is, we need to send oxygen-rich blood to that area, right? So your nervous system is ultimately what makes that decision and makes these adjustments, right? As soon as I start moving fast, my sympathetic nervous system is going to kick in and start sending blood and other nutrients towards the areas that need them, which would be the muscles. But when I sit down and relax, my parasympathetic nervous system is going to take over. It's going to divert blood away from my muscles and send it towards my liver, my kidneys, my stomach, etc. Okay? So, we can actually kind of skip this slide and jump back into... I got a little bit ahead of myself because I get excited about the sympathetic nervous system. Because I'm kind of a sympathetic nervous system dominated person, which is why I get stuff done. But anyways, so these two slides, I'm not really worried too much about you all looking at this information because this is more sort of global, like overall nervous system stuff, and we're sticking to the exercise physiology things. So we're going to skip really these slides as well and jump to, this one is kind of a summary of what I just talked through a couple slides ago, breaking down the different divisions of the nervous system. So you might want to pause it, read this over because I've already talked about it in the previous slide, okay? And now we get caught up to talking about the autonomic nervous system, which again is divided into the sympathetic and the parasympathetic. So on this slide, it gives you a few, not all, but a few of the things that these two divisions of the nervous system innervate or stimulate. So the sympathetic nervous system nerves, we should say, supply the heart, smooth muscle, sweat glands, and internal organs, okay? While the parasympathetic nervous system also supplies the chest cavity, the abdomen, the pelvic region, okay? There's overlap here because, as we'll see on the next couple slides, right, the heart has dual innervation from both the sympathetic and the parasympathetic. When we're resting, the parasympathetic nervous system slows our heart down, right? Remember we said the intrinsic rate of depolarization of the heart is 100 beats per minute. So without any nervous system stimulus, the heart would beat at 100 beats per minute. Now, most of us, all of us probably, when we're resting, our heart rate is closer to 60 beats per minute. And that's because the parasympathetic nervous system is slowing the heart down. Now, when we're exercising, parasympathetic nervous system stimulus goes away, sympathetic nervous system stimulation moves in, and that drives the heart rate up over 100 beats per minute. So again, most tissues are going to have both sympathetic and parasympathetic innervation, as we see here on this slide, okay? Now, for your critical thinking assignment, I'm going to ask you to look at this slide in particular, yeah, and think about, for an activity that you're doing, like what effect the sympathetic nervous system is going to have to make that activity possible. So you see here, the yellow lines represent sympathetic innervation. The green represents parasympathetic. Now, in a lot of cases, these different tissues or organs are going to have both green and yellow, right? So we talked about the heart a second ago. It gets dual innervation. The lungs, again, they're going to get dual innervation as well. When we're relaxing, our breathing can be slowed down. And when we're exercising, our breathing is slowed up because of that dual effect of fight or flight, rest and digest. Something you might not have thought about is your eyes, right? When we're exercising, our eyesight actually becomes more, just for lack of a better word, it's going to improve, okay? Because the sympathetic nervous system is going to cause your eyeballs to dilate. They're going to open up, more light's going to come in, that's going to allow you to see more, right? So if you're fighting for your life, that's going to be an advantage, okay? When you're resting, pupils are going to close, and that's actually going to allow you to eventually go to sleep potentially, because less light is going to get into your eyes. That's going to allow your brain activity to slow, and you could fall asleep, right? So again, dual innervation there. What else can we pick out? Let's pick out one more. Now, muscle is not shown on this particular diagram, but same situation. When we're exercising, the blood vessels that surround our muscles, they're going to open up due to the sympathetic nervous system stimulation, and that's going to allow more oxygen-rich blood to get in. When we're resting, the blood vessels are going to constrict due to parasympathetic stimulation, and that's going to divert O2-rich blood away from the muscles, allowing it to go towards the digestive system, etc. Okay. So again, I want you to pick out a couple. I think I say 3 on the critical thinking assignment, and just I want you to critically think. That's kind of one skill I'm trying to get you all to learn and use in this class. Is not just me telling you something and you repeating it, but me giving you some information, and then you thinking about that information and developing your own answer. Okay, that's a skill that is really, in our world, is being taken away from people, and I want you all to gain that skill, not lose it. So that's where we're going to do that particular assignment, the last one of the semester, and I've been trying to challenge you all with that all semester, actually, without telling you. Okay, anyway, moving on. So what we're going to do now is sort of jump to the second major topic, and that is how nerves supply muscles. Okay, so as we see on this slide, one nerve does not just supply one muscle fiber. One nerve is going to touch and supply a lot of muscle fibers, right? As an example, one nerve might innervate 250 million muscle fibers. Now, muscle fibers are very small. We have a lot of them. So 250 million sounds like a giant number, and it is, but it's not quite as large as it sounds right now, okay? However, this is a term that you need to learn, and that is a motor neuron. So a motor neuron is a nerve that innervates muscle, right? Think motor is movement. A motor neuron is a specific type of nerve that stimulates muscle, okay? A motor unit then is made up of, we see the definition here in blue, one motor neuron, and every muscle fiber it touches is known as a motor unit, okay? So we have thousands, millions of motor units in our body. Again, that's a motor unit is sort of referred to as the functional unit of movement. One neuron, one motor neuron in every muscle fiber it touches is called a motor unit, okay? We have a lot of different types of motor units, as we'll see here shortly. However, motor unit types are related to muscle fiber types, as we'll see here in just a second. Okay, so this is a good picture of a motor unit, right? One nerve, the alpha motor neuron, and all the fibers that it touches. Okay, now in this picture, we see that a muscle is made up of several motor units, right? This is an important picture maybe to talk about for a second for a topic coming up soon. We're able to scale or manipulate the amount of force a muscle produces by controlling how many motor units are activated at a given time. If I had a 5-pound dumbbell in this hand, right, and I was going to curl a 5-pound dumbbell, I might only need a couple motor units. So maybe let's just say, for sake of an example, this one and this one are activated, allowing me to move 5 pounds. Now, if I then graduated to like a 30-pound dumbbell that I'm going to curl in this hand, I might need all 5 of the motor units, right? So we're able to scale the amount of force we produce by recruiting either less or more motor units, and that term is known as motor unit recruitment, which I think is not on the next slide. Darn, I thought I had a great transition, but I blew it. Sorry, people. We'll get to that in a second. What we want to talk about really quick is, as a subtopic, is we want to think back to that sliding filament theory, and we looked at the process that influences muscle contraction. We skipped a step, and that is the nervous system step, which is what we're going to kind of quickly go through here, right? It is related to this. Now, what we're looking at here, if we zoomed in on this part of the muscle fiber, it would look like this, right? So the nerve doesn't actually touch the muscle fiber. It sort of fits in a little, what's called a cleft, okay? Now at the end of this nerve, as the electrical impulse comes from our brain down the nerve, it stimulates the release of what is known as a neurotransmitter. And the specific neurotransmitter in this case is called acetylcholine. Don't need to remember that word. That's just what it's called. Acetylcholine then travels across this space, and it's going to bind to receptors on the sarcolemma, or the muscle fiber membrane. Okay. Once that happens, basically there's going to be an electrical impulse generated on the surface of the muscle fiber, and it's going to sort of travel like this, shoot across. It's going to travel into the muscle fiber, into what's called the T-tubule, and the T-tubules are surrounded by the sarcoplasmic reticulum. Do you remember what is stored in the sarcoplasmic reticulum in the muscle? I'll give you 2 seconds to think about it before I tell you. And actually, I'm going to point to it. Well, it's not here, actually. Calcium. So to make a long story short, the electrical impulse travels down the nerve, the motor neuron. Acetylcholine is released, which binds to the muscle fiber. That's going to generate an electrical impulse that ultimately stimulates the release of calcium from the sarcoplasmic reticulum. The calcium, you might remember, then binds to the troponin. Troponin moves tropomyosin out of the way, allowing actin and myosin to bind. Okay. Now, as long as we're consciously thinking about movement, the electrical signal is going to keep coming. Boom, 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 boom. And that's going to allow calcium to stay present. As soon as we withdraw the thought of movement, the electrical impulse from here is going to stop. Calcium is going to be pulled back in to the sarcoplasmic reticulum, and actin and myosin won't be able to bind anymore. Okay? So that process that I just talked about is described in detail on this slide here. Okay, so again, hit pause. This goes into a lot more detail than what I just went through, but I think for this class, what I just went through verbally is enough, you know. But again, read this and cross-reference it against what I said so you can hopefully understand it a little bit better, right? We can't have contraction without excitation, which is why excitation coupling is what they called it in the previous chapter. They're bound together, right? In order for us to have muscle contraction, we first have to have the excitation that comes from our brain to allow the mechanical process of contraction to occur. Action potential, just in case you're wondering, is another word for like electrical impulse. I said electrical impulse. Action potential would be a suitable replacement for the word that I used, okay? Okay, so let's jump back to motor units. As I mentioned, there are a few different types of motor units. Now, motor units are basically going to contain only one specific muscle fiber type. So if we jump back to this slide, sorry, these would only be type 1 muscle fibers or type 2, but you can't have a mixture of 1 and 2, right? So one neuron can only innervate a bundle of type 1 or a bundle of type 2. But because of that characteristics, that allows us to label motor units as either type 1 motor units or type 2 motor units, okay? And here's where we're going to start getting some crossover, right? All of those characteristics that we learned about muscle fiber types also would apply to motor unit types because muscle fiber types make up motor units, right? Again, it's a crossover. They blend together. So you don't have to really learn anything new with this. You just kind of are going to recall what we talked about last chapter, and it's going to apply here as well, right? So motor unit types are going to have certain abilities to produce force, either high or low, or they're going to be have good fatigue resistance or poor fatigue resistance based upon the muscle fiber type that is included in that motor unit. So again, here are the characteristics of each motor unit type, and they're going to be the same as the characteristics of the muscle fiber type. And it actually makes it easier because they have the same name. So a type 2A motor unit is made up of type 2A muscle fibers. Type 2X motor unit is made up of type 2X muscle fibers. Type 1, the same, okay? Now, and that kind of jumps back to that whole motor unit recruitment idea. If we're doing an activity that requires type 1 muscle fibers, we're only going to recruit the type 1 motor units. There's no reason for us to use the type 2X motor units for activities that don't require those types of muscle fibers. Often, type 1 motor units are smaller because, again, there's no reason to produce a lot of force if you're using type 1, so you don't need as many muscle fibers. Where type 2X motor units often contain more muscle fibers because force production or the ability to exert force is higher with those motor units. So activities that require a lot of force production, they're going to need more muscle fibers, right? It's going to take me, I'm going to need more muscle fibers to deadlift 400 pounds than I would to jog around my block, right? So if I'm jogging, I'm going to be using mostly these motor units. If I'm deadlifting 400 pounds, I would actually be using all three, right? Full motor unit recruitment is required when we're at maximal force production, where submaximal force production might only utilize type 1 or type 1 and type 2A, but probably not all three, okay? Again, it's the amount of force can be scaled based upon the need by how many motor units we recruit, okay? Again, this sort of gives you the characteristics, and this should match the muscle fibers, so we don't need to go through this, but again, you might want to hit pause and go through this chart again quickly. What the all or none principle states is once a motor unit is activated, every fiber that motor unit touches is going to be activated. So if I jump back to say this slide, I can't just activate one of these fibers, right? If one of them is activated, all of them are going to be activated because they're all stimulated by the same motor neuron. So once this motor neuron sends the signal, every single fiber it's going to be attached to is going to produce force, right? So that's what the all or none principle states, okay? They're all going to activate synchronously, which means at the same time. So we can't grade force by only activating a portion of fibers in a motor unit. We grade force or change force by activating more than one motor unit, right? If I need small amount of force, I'm just going to innervate this one. If I need maximal force, I'm going to go with all of them. A couple other ways that we can change force is, one, the one I just mentioned, the number of motor units. If we're deadlifting 400 pounds, we're going to recruit more motor units than we would if we're deadlifting 135, okay? We can also increase the frequency of the signal, right? So if I jump back to this slide, if I'm deadlifting, say, I don't know, 225, which is heavy, but not super heavy, the signal might be going, I'm going to try to use my finger, this fast. Boop, boop, boop. But then if I try to deadlift 400, it's going to go faster. Boop, 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 boop. So the faster the signal travels down this motor neuron, the greater the force production will be, right? So when I'm doing a maximal deadlift, the frequency is going to be much faster than if I'm doing a deadlift of 135, right? So those are the two ways we can manipulate the amount of force we're producing, by either recruiting more motor units, or by two, increasing the frequency of discharge. Now, somebody who's not resistance trained, their frequency is going to sort of be blunted and it's going to be slower. But by doing strength training, especially heavy loads, we increase the ability for our brain to speed up that frequency, which allows us ultimately to be stronger. One reason why we get stronger when we lift weights is because our body gets better at this. We can have an increased frequency, and we can also increase the number of motor units that we activate. Somebody who doesn't strength train, their frequency is going to be slow, and their body's not even going to know how to recruit motor units in a coordinated fashion, right? It's kind of like riding a bike. When you're riding a bike, you don't have the coordination to stay on the bike well, because your body just doesn't know how to program motor units in that coordinated fashion. But by practicing riding a bike, ultimately our brain learns how to do it. Same thing actually happens with lifting weights. We all have the ability to lift heavy weight, but our body just doesn't know how to do it because we've never done it before. But the more that we practice strength training, the better our nervous system gets at activating muscles in a coordinated fashion. And that allows us to be stronger with the muscle that we have, right? When you lift weights for a prolonged period, you get stronger without putting on more muscle. And that's what's known as the neural adaptation. And that's what I'm just talking about. Your nervous system becomes better at activating the muscle you have, which leads to you being stronger. Size principle, sort of, we've already touched on that, but that goes back to this slide. We're always going to recruit the smallest motor units first, because why would we want to recruit every muscle if we only need a couple? That's a simple way to put it. As force production needs are increased, we recruit progressively larger motor units. And I sort of already explained that with this slide here, right? If I'm lifting a little weight, I might use the small. If I'm lifting a medium weight, I might use a small and medium. If I'm lifting a maximal weight, I'm going to recruit the largest motor units. That is what the size principle refers to. Okay, we're always going to start with the smallest and progress to the largest every time, no matter what we're doing. Even if I'm doing a maximal deadlift, my body's still going to try to do it with the small motor units. They're going to be recruited first. They're not going to be able to accomplish the task. So I'm going to then start recruiting the larger ones. But they're always going to start with the smallest and progress to the largest, no matter what I'm doing. Okay. Now, one thing I'll just say about this only in a maximal lift would they fire simultaneously. Usually motor units do not fire at the same time, and that helps us maintain force production for longer periods of time. One fires, and then once that one gets tired, another one fires, and the original one rests, and they sort of imagine they kind of alternate back and forth. I can only do that if my force production is sub-maximum. Now, if it's maximal force production, they are all going to fire simultaneously, and that's why you can't maintain or sustain maximal force production as long as you can sub-maximal force production, okay? We're getting into the weeds a little bit here. I don't want to confuse you all too much, so I kind of want to move on from this topic before we get too in the weeds and you get overly confused. Just to touch on this briefly, one way that we do get fatigued is what we call neural fatigue, okay? Because that process we've been going through, we can only sustain that for so long, right? And you all have probably experienced like mental fatigue, where the idea of continuing to exercise is too much for your brain to overcome. And that, to me, is sort of a symbol of this nervous system fatigue becoming a factor, right? If we jump back to here, eventually your brain is going to be tired of sending this signal over and over and over and over and over again. And that is, again, sort of a manifests itself as being mentally fatigued. So, to put a bow on that, the nervous system is definitely a part of us experiencing fatigue when we're exercising. All right, last topic here is the reflex arc, and I'm going to hit this just quickly. We do have a way to sort of bypass the brain, where usually we have to use our brain to think about muscle contraction, but there are instances where muscle contraction can automatically occur. We call that a reflex, okay? Reflex arcs are mediated in the spinal cord. They don't reach the level of the brain, okay? And a good example of this is if you touch something hot, right? You automatically pull away. You don't have to think, oh, this is hot, I need to pull my hand away. It automatically occurs, okay? And this is related to pain receptors. There's what we call a reflex arc, where the sensory receptor is stimulated. You feel the pain, all right? That information is sent to down a nerve into the spinal cord, okay? Where there is an automatic stimulation of the outgoing muscle fibers, the efferent fibers that cause the contraction of that muscle, right? So notice here, the reflex arc basically goes, you feel the pain, pain receptor sends information to the spinal cord, which then reflexively activates the muscle fibers in that area to promote contraction to pull you away from the pain, okay? That explanation is summarized here in this slide. Again, this gets a little bit too complicated for what I think you all need to understand at this time, but just, I guess my point is, not all muscle contraction is conscious. We do have these reflex arcs that really serve as a protective mechanism to help us avoid damaging our tissue due to the experience of pain. What the last topic is a few specialized receptors in our skeletal muscles, and those are called muscle spindles and Golgi tendon organs, okay? So we call these proprioceptors. They are receptors that help us adjust for force production, and they provide our nervous system with input to help us adjust the amount of force we're producing, etc. Okay, so there's two of those. We're going to hit these two, and then we're done for the day. First one is a muscle spindle. So a muscle spindle is a specialized muscle fiber that is located inside a muscle. It looks like this, right? So we have normal muscle fibers here. Laying right along the muscle fibers are these muscle spindles, and these are basically specialized sensory organs that are sensitive to stretch, okay? So when a muscle is stretched, these muscle spindles are stretched as well, and they provide feedback going to the nervous system. The afferent division, remember, afferent is ingoing towards the central nervous system, okay? And they help us basically adjust for force production. And they kind of provide for a way to resist injury. And basically the way a muscle spindle works is when a muscle is rapidly stretched, it automatically contracts to resist that stretch, okay? Stretching a muscle rapidly will increase the force production in that muscle, right? That's why you all might have heard of something like it. Well, let's think about a broad jump, right? You can jump farther. I'm going to try to show you this. If I just stand here and try to jump forward, I'm not going to be able to go very far. But if I do an eccentric contraction on muscles and then jump forward, I'm going to be able to jump a lot farther, okay? The reason why that occurs is because when I do that counter movement, I'm stretching my muscles, which is going to then increase the force production in the concentric phase of my jump, right? Where if I just stand there and jump, I'm going to lose the increase in force production that comes from the stretching of the muscle spindles. Now, we utilize that in strength training all the time, right? If I'm doing a bench press, when I go down, I'm stimulating the muscle spindle, which helps increase the force production in the upward phase of the bench press, okay? So these contribute all the time, right? It's very hard actually for us to produce force without stretching a muscle first. Jumping is probably the best example of when we could do that. But with strength training, we're almost always going to stretch a muscle before we contract it. And the muscle spindles are activated during that stretch, and they help increase force production. And we call that's called the stretch reflex. Okay, that's kind of a specialized reflex where the muscle spindles respond to stretch, and they essentially then tell the nervous system, we were rapidly stretched, increase neural input to this muscle that was stretched so we can produce force. Pause, read this slide. We then have, well, actually, this is another example of the stretch reflex. When you go to the doctor and he uses the hammer to hit your patella tendon, the reason why your leg jerks is because hitting this tendon causes the muscle spindle to be stretched, and that causes a reflexive contraction of your quad, which is what causes your leg to kick forward slightly. Last topic then is the Golgi tendon organ. This is the other proprioceptive organ that is located not in our muscle. These are located in the tendons. These also serve as a protective mechanism, and they are sensitive to tension. Now, the muscle spindle was sensitive to stretch. The Golgi tendon organ, or the GTO it's called, is sensitive to tension. When the Golgi tendon organ perceives tension, it actually reduces force production. Muscle spindle increases force production. Golgi tendon organ reduces force production. So it's inhibitory in nature. Muscle spindle stimulatory, Golgi tendon organ inhibitory. So this is sort of a picture of where the Golgi tendon organ will be found. Again, it's in a tendon. And the point of this is if the tendon is feeling a lot of tension, as a protective mechanism, the body does not want the tissue that is feeling tension to tear, right? So force production to that muscle is reduced to prohibit the tension that is perceived from causing an injury. Now, some think that one reason why people who are not well trained with strength training cannot produce a lot of force is because they have a very strong inhibition from their Golgi tendon organs, right? Which is probably a good thing, because if somebody's not well trained in resistance training and they try to bench press 135 pounds, they could tear a muscle, right? The tension is going to be too high because they do not know how to use their muscles in the appropriate way to move that weight, okay? So the Golgi tendon organ is there to help minimize the risk of injury. Now, as somebody becomes more well strength trained, another of the neural adaptations is there is reduced input from the Golgi tendon organ, right? This is inhibitory, which means it's going to shut down muscle force production abilities. So if we eliminate or reduce the inhibition from the Golgi tendon organ, the muscle will be allowed to produce more force, right? So as we become more trained from a resistance training perspective, the effect of the Golgi tendon organ is lessened, which allows us to produce more force and therefore be stronger, okay? This also functions as a reflex arc, and it is mediated at the level of the spinal cord, as the picture shows here. It does not reach conscious thought, which would be at the level of the brain. It's mediated more in the spinal cord, okay? I know that was a fast run through these two things. I guess I'll just jump back and just summarize again. Muscle spindle stimulates increased force production. Golgi tendon organ inhibits force production, but through strength training, we lessen the impact of the Golgi tendon organ, which allows us to be stronger, to put it simply, okay? So that's going to do it. We have, as usual, our last set of study questions, last critical thinking assignment. I do want to remind you all about the extra credit labs. There are 2 of those available. They're each worth 20 points, so a lot of you need those points. Take advantage of those labs. They're going to be the same format as the previous ones. Watch the video, collect the data, answer some questions, do some calculations potentially. And then as a reminder for the final exam, same format. It's not cumulative. It's only going to cover the information since it's the second exam. And it's going to be available for several days. So I'll have it posted and available for you all to take on Monday the 14th through 8 o'clock on Thursday the 17th. And then I'm going to try to get the grades posted pretty quick after that, okay? I will also announce that if you do the course evaluation, if I get 90% compliance, which means 90% of the class has to do the course evaluation, I'll give everybody 5 extra points, bonus points on their final exam, which again, don't take it for granted that you don't need it, because that could be the difference between a B+ and an A-. You never know, okay? So that's it. Any questions? Let me know. Otherwise, talk to y'all soon. Bye-bye.